President of the American Geophysical Union, and I have the distinct pleasure of being session chairman for this Frontiers of Geophysics session this evening. The Frontiers of Geophysics is a long-standing tradition at AGU that dates way back to our Jack Tar days, but was dropped for a number of years, having been suddenly resurrected last year with Don Anderson's Frontiers of Geophysics talk. And so now we have tonight the second year in a row in which we've been able to revive this wonderful tradition of providing a very interdisciplinary talk from a very distinguished speaker on a topic that is of interest to all members of the AGU. Our speaker tonight is Dr. Ed Stone. Dr. Stone has been for many years on the faculty at Caltech. He did his research work in the area of cosmic ray physics, but probably is best known to most people here as the project scientist for the two Voyager spacecraft. As everyone recalls, those spacecraft visited the outer planets, Jupiter, Saturn, went on to Uranus and Neptune, and the information that has been reaped from those two satellites far exceeded the expectations, I'm sure, of even the project scientists at the time they were launched, but have been the fodder for many scientific papers, many beautiful images, and much public imagination in the time since then. Based on the great success of the Voyager mission, Ed Stone was then tapped to become the director of JPL, a position which he holds right now. So without further ado, I'd like to introduce Ed Stone with his talk, Sampling the Solar System.
Thank you. And sampling the solar system. Well, that's certainly a frontier of geophysics. I think it's frontier of geophysics has been expanded with the beginning of the space age over almost 4 decades ago. And in those 4 decades of exploration, the solar system has been revealed to be a remarkably diverse place, much more diverse than I think anyone imagined before the space age began. A diversity that each succeeding mission actually elaborates and expands. Now, many individuals have contributed to what we've learned about the solar system. I can't possibly acknowledge all whose work I'm going to be talking about this evening. The first era of exploration began 38 years ago this month when Mariner 2 flew by Venus. Now, the challenge in the first era, and if we could focus that a bit, the challenge in the first era was just getting to another planet. In fact, Mariner 2 lived just a few days beyond its encounter. It was a 100-day journey to Venus, and in 1962, that was a challenge. Then came Mariner 4. In 1965, returned the first 21 digital images of another planet. That in itself was the main accomplishment. Those 21 images covered much less than 1% of the surface of Mars, and they came back at a data rate of 8 1/3 bits per second. The challenge in the first era was just getting there and getting any data back at all. But that era laid the foundations for what I call the second era, and that was finding what was out there. Once we knew we could go, once we knew we could communicate, then the challenge was how do we develop these systems which, in fact, no matter what's there, we have a chance of capturing it. And so that meant large observatories with a wide array of instruments, large bandwidths, autonomous spacecraft, which in fact provided a global view of the many diverse worlds in the solar system. And that era is not over. These eras don't stop and start discreetly. In fact, they will continue. But in fact, this era, which is sort of the global survey, the global exploration era, has really set the stage for what I call the third era, where the challenge now is different again. The challenge now is to move from global to local and to go often to land and eventually to bring samples back. Now, again, this era didn't immediately start on a particular date. We're actually Viking, after all, landed on Mars back in 1976 as the first landing on another planetary surface to search, of course, in this case, for any evidence of life past or present. And as everyone knows, there was no evidence for life on Mars, as could be examined by the set of experiments that Viking lander was carrying. About the same time, though, about a year later, our concept of the robustness of life was greatly altered by oceanographers who were looking at deep sea vents and discovered that deep under the ocean there were flourishing colonies of life which did not depend upon photosynthesis but upon the chemical energy coming from the interior of the Earth. And since that time, we now find life in water, even if it's within ice in Antarctica, within rock that comes from deep wells, or even in acidic rivers. Wherever there's water on Earth, it appears life has found a way to in fact thrive. And that takes us back to the issue of where else in the solar system might there have been life, and that means follow the water. Where was there water? Where perhaps is there water? And how can we sample these other environments in the solar system? That obviously takes us back to Mars, because at one time Mars did have a lot of water on its surface. This is a recent Mars Global Surveyor image, which certainly suggests that there could well have been flowing water in this canyon at one time. And in this Viking image, certainly it looks like that might have been a dry lake. That might be a dry lake bed. Well, the Mars Global Surveyor, which is now in orbit around Mars, has on it a laser altimeter, which can provide the first accurate topographic map of Mars. It has now quantified what has been known, that is that the northern hemisphere is much lower, about 3 kilometers lower than average. The southern hemisphere is old, and about 3 kilometers higher than average. This is color-coded by altitude. You can see the scale over here in kilometers. Blue is about -4, and red's about +4 kilometers. The one question, of course, is what is the nature of this northern plain? If one looks in a polar plot, and if there had been an ocean about 1,500 meters deep, it would have filled this part of the North Polar Cap. Now, whether or not there was an ocean is a subject of great debate. That is, we know that there are large canyons which are feeding this basin, but whether or not the water was standing there for a sufficient period of time to have actually provide that opportunity for the origin and evolution of life is unknown. There has been a search for ancient ocean shorelines, and no evidence that, in fact, people have accepted that it's clear that there is such an ocean, but a shoreline. On the other hand, it's not yet, I think, clear what such a shoreline should look like, given the rather different character of the water cycle on Mars compared to Earth, which is the model we have for such searches. So we don't know if there was standing water on Mars, but that's where it would have been. And in fact, it was at the outlet of a large channel where Mars Pathfinder was landed back in 1997, at the outlet of one of these large channels in an ancient floodplain. And with its small Sojourner rover to begin the first in situ roving of the surface, and a very simple beginning of geology in terms of looking for the composition, the chemical composition of the material which is there. What Sojourner and the Pathfinder basically showed was, in fact, there are rounded pebbles. Boulders certainly have the character that one would expect from having been carried by massive floods. The dust is magnetic, as might be expected from iron having been leached. But again, it does not mean that the water was there in a persistent way, but just that at least that there were large floods which created these large canyons. Now, one question, of course, is how long was the water there? When was the water there? And it turns out that Mars Global Surveyor has given us another set of data which may give us some clue as to what some of the circumstances might have been with respect to the early atmosphere of Mars. We're in a very elliptic orbit for a while, which put us at much lower altitudes than had been planned, and that meant that the magnetometer could actually make new measurements, a new search for the Mars magnetic field. What was found was there is not a global magnetic field today, but there are, as shown on this map, there are regions in the ancient, older part of the Martian terrain where there is a remnant magnetic field. Also, it's clear from these two large impact basins and the absence of such remnant magnetic fields around them, that suggests that the magnetic field, the global magnetic field, which was, say, in this model, would have been there at the time this part of the surface solidified. That magnetic field was no longer there at the time that this area was impacted and then re-solidified. That suggests, with this interpretation at least, that Mars had a global magnetic field for less than about 500 million years. And once the magnetic field, once the interior cooled to such an extent there was no longer a global magnetic field, then there was no longer a protection of the atmosphere from the solar wind. And that could have contributed to a marked change in the atmospheric pressure on Mars. Now, the water today is not in liquid form on the surface. The water which must have carved those great canyons is not evident. But there is some water evident on Mars, of course, in the icy polar caps. This is the North Polar Cap, and the laser altimeter on Mars Global Surveyor has provided a very accurate topography now so that we know exactly how much water ice would be in this polar cap. This has a vertical exaggeration to it. The average height of this polar cap is about 1 kilometer. The maximum height is about 3 kilometers. There's about as much water ice in this polar cap as half of what's in Greenland. And that's about maybe on the order of a tenth of estimates of how much water was originally, must have been on the surface of Mars, at least on some occasions. The South Polar Cap, again, this is a color-coded laser altimeter map where the redder colors are higher altitude. It's a fairly large, the visible polar cap is a small region. This is a much larger region. And if this is really indeed an icy polar cap, it contains on the order of 1 to 1.5 times as much water ice as Greenland. Added to what's in the North Polar Cap, it's still not as much water as one believes must have been there. But there is quite a bit of water locked up in these two polar caps today. Of course, it's certainly likely that there's water underground in the form of permafrost or deep enough underground in the form of liquid water. And that's what makes images like this so enticing. This was one of the earliest images coming back from Mars Global Surveyor that showed this evidence of seepage, what appeared to be seepage from the wall of an impact crater. And certainly from the outline of the deposit, which is on the floor of this crater, certainly looks like something had ponded there at one time. As I say, today it can't be liquid water, but certainly it looks as though at the time, whenever this material was put in place, that it was flowing. Since that time, of course, Mike Malin and Edgett have reported other features, such as these gullies in the sides of craters, and in this case, multiple gullies which have informed the craters, along with the aprons which have formed at the base of the craters, apparently from material which is coming from a layer only a few hundred meters below the surface, much closer to the surface than any models would suggest one would expect to find liquid water. And again, there is a large debate as to whether these are formed by liquid water or if there is some other way to form these features, which certainly look so much like water-formed gullies. If I can now could I have the video, please? Could I have the video, please? Oh, you're there? Okay, go. This is Gorgonum crater. It's the one I showed you in one of the slides, and this will just show you one of the features about these gullies is they appear only on the colder face of the crater. And we'll see that you'll see that the gullies on this face of the crater, the pole-facing, if you like, faces of the crater. These are the long gullies in that one slide I showed. Then on the other warmer side, no evidence for these gullies. and they found, I think, well over 100 examples of these kinds of features in various craters and canyon walls. The more recent, just recently, last week, in fact, they published some new results having to do with layered terrains in some regions. This is, I think, Arabia, and here you can see the stair-step layered terrain, which is certainly very characteristic of sedimentary deposits. Very, very regular in this particular region, stepped, layered deposits. The question, of course, is what formed these deposits? Where did this material come from? It's a puzzle where this material came from, because there are no channels bringing it in. This is one other example, Candor, which shows a somewhat less regular layering, but still very clear, distinct sedimentary layers, certainly suggesting the presence of standing water in these regions on Mars at one time, several billion years ago. Now, this is not unlike the gullies, which may be fairly recent. This was, in fact, several billion years ago, not recent at all. That's it for the video. Thanks. So one of the big questions is, where did this material come from? How did it get carried to these regions? Typically craters and some of the canyons have these features, but it certainly has, again, changed our view of Mars dramatically. There had been some indication from earlier Viking data of layering, but this is now by far the most persuasive evidence that there has been sedimentary deposition on Mars, and suggesting, at least for a while, presence of standing water. Again, these are very new results and the subject of a great deal of scientific debate in trying to sort out what these features are. But in any case, it's clear one of the keys to understanding regions like this is to sample them and try to date them. So sampling regions like this, which are potentially very interesting from the standpoint of understanding the climate and on Mars, and potentially the possibility of the origin of life on Mars, is one of the challenges for sampling in the solar system. And landing in a place like this is going to be very challenging. Well, the next landers, in fact, are now planned for 2003. 2 rovers, about 150 kilogram rovers, quite a bit more capable than the 11 kilogram Sojourner rover, much more complex set of spectrometers on the rover, and the capability to transmit directly to Earth, so it does not have to stay near its lander. Like Pathfinder, it will land on airbags, and there'll be 2 of them, and of course one of the key questions is which sites to pick to land these 2 rovers. But with an airbag system, the precision of the landing still is not adequate to be able to get into some of the most interesting spots in a safe way. That will be part of a longer-term exploration plan. So 2001, this April 7th, is the next Mars orbiter, carrying both a thermal infrared mapper as well as a gamma-ray spectrometer. Then in 2003, the pair of Mars exploration rovers. 2005 will be the next orbiter, which will have a much higher resolution infrared mapper on it and a much higher resolution imager, visible and near infrared imager, perhaps 20, 30, 40 centimeter resolution, as opposed to about 1.5 meters for the camera on Mars, on the Mars Global Surveyor. Also in 2003, the European Mars Express will be in orbit around Mars and carrying Beagle 2, another lander, which will be dropped to the surface on airbags. And the Japanese will have their Nozomi mission. So 2003 is going to be a very exciting time for Mars. Then 2005, as I said, is the next orbiter. Beyond that, the plan would be every other opportunity to land increasingly capable landers, eventually leading to the capability of returning a sample. and of course supported by the ever-increasing capability of the orbiting spacecraft, which will tell us where these most interesting spots are. But we obviously need to learn how to land much more precisely than we can today with the systems that we have currently. So that will require development of much more precise and controlled landing systems. Well, Mars is clearly one place where there was water, perhaps where there is water. Further out in the solar system is another possibility, and that's at Jupiter with its two moons, Io and Europa. This is a Voyager image from 1979, and of course this clearly characterizes the distinctive characters of these two moons orbiting Jupiter. And this, of course, was one of the major surprises of the Voyager-Jupiter encounter, was the volcanic activity on Io. It had been actually predicted just a month or two before that Io could be tidally heated, but I think it was really quite a remarkable surprise to find that tidal heating created the most volcanically active body in the solar system. This is a Galileo image showing several of the volcanic plumes. And again, just to illustrate how this heating, how strong this heating is, can we focus that a bit? I can see that the printing down in the corner is not clear. Thank you. This is a large volcanic caldera. You can see the scale, 50 kilometers. So this caldera is some 150 kilometers across. I mean, the big island of Hawaii would fit inside of this crater. So Kilauea is a tiny little crater compared to the size of these craters. And this, of course, is a lava curtain, some 15 kilometers long and about 1.5 kilometers high. The height of the walls of these craters is on the order of 1 to 2 kilometers, to give you a sense of the scale of this immense volcanic feature up near the North Pole of Mars. This image, and then 3 months later, notice where the lava curtain is in this image. 3 months later, that's where the lava curtain was. 3 months later, it has moved. This is a remarkably active body, heated by tidal flexing of its crust, something on the order of 30 to 50 meter flexing of its crust every 1.8 days. Now, the point of this is that same tidal flexing is operating at Europa, just not as intensely, because Europa is at about 10 Jovian radii, Io is about 6. And when Voyager flew by in 1979, it found this surface, which was the smoothest surface in the solar system. The dark streaks were literally just streaks a few hundred meters high, and certainly suggested the possibility that this might be an icy crust over a liquid ocean, heated by tidal flexing of its crust, again on the order of a 30-meter tidal flexure every 3.6 days. Well, of course, the Galileo mission has returned, can fly much closer to Europa than Voyager did, 100 to 1,000 times closer, and has really has allowed us to really understand the nature of this world and all the cracks which have developed in the icy surface. This is an enhanced color image showing that there are deposits associated with these cracks, and the cracks also suggest that the crust itself is rotating with respect to the solid interior. There are regions like this where there is upwelling, which has broken through the icy crust, again depositing some other material besides just water ice on the surface. And a region like this where the highly linear cracked surface has been broken apart into rafts and evidently floated around on the surface of Europa, at least with some reasonable mobility at some time in the past. Of course, the question is, how long ago did this happen on Europa, and are there any places like this today? Since Galileo is in orbit around Jupiter, it flies by any one satellite only every 2 months or so, and can obtain resolution like this only for a spot on these bodies at closest approach. So we have very small amount of coverage of any of these satellites from Galileo, and so we can't possibly know the extent of the current state of this surface globally. That requires an orbiting spacecraft around Europa. That is a major challenge, to go into orbit around Europa, and the radiation environment at Jupiter is remarkably intense. Galileo, which has been in orbit now about 5 years, has accumulated about 300,000 rads of radiation. An orbiter around Europa will accumulate about 10 megarads of radiation. So this is a major engineering challenge, but if one could fly, for instance, a laser altimeter, one could measure the flexing of this crust, and that will provide some information about how thick the rigid portion of this crust is. One could use a radar to look for the water-ice interface. And of course, from Galileo, the magnetometer on Galileo has told us there is an induced magnetic field, which reverses itself every 5.5 hours, certainly suggestive of a fluid, conducting fluid, very close to the icy surface of Europa. So an orbiter is a key next step before one would ever think about trying to sample this surface. But it's certainly, if there's a liquid water ocean beneath this hard icy crust, it's got to be a world where we'll want to sample in the future. The next step, though, will be to do a global survey so we know where to look and how to look in terms of sampling this world, which may well have liquid water. Now, further out in the solar system, Saturn, 10 times as far from the sun as the Earth, much colder, but it has a moon, Titan. This is a Voyager image from 1980, which is very hazy because, in fact, there's a thick photochemical haze, organic polymer haze, that blocks visible view of the surface of Titan. Titan, of course, has a very dense atmosphere. The surface pressure is 1.5, 1.6 times that here on Earth, mainly nitrogen-like here on Earth, but with a trace of methane, which photochemistry and radiation is converting slowly but surely to more complex organic molecules, some of which become large enough, polymerized, so that in fact they provide this opaque haze. And some of it is believed to be ethane, which at the surface temperature and pressure conditions on Titan would be liquid. So there is even suggestion that there might be lakes of liquid organic material on this world. Now, this is a Hubble image taken in the near infrared around 1 micron, which can, in fact, sense some difference, some small contrast differences on the surface of Titan. I think the contrast range here is about 4%, so it's not large, but it certainly suggests that there may be darker and lighter regions on the surface of Titan, as might be consistent with regions which are lower and less reflective because of their hydrocarbon coatings. The Cassini mission is on its way to Saturn. It flies by Jupiter on December 30th, at the end of this month, to get its last gravity boost onto Saturn. It arrives in Saturn in July of 2004 and is carrying a radar system which can be used to map the surface of Titan as it flies by Titan in its orbit, as it orbits Saturn, but flies by Titan 10, 20, 30, 40 times, and of course is carrying the Huygens probe, the ESA Huygens probe, which we dropped into the atmosphere of Titan with a set of instruments designed to measure the organic chemistry that's occurring there today. And this artist sketch, it suggests we don't know exactly what kind of a surface the probe will finally find as it drops down into the atmosphere of Titan. This will be our first in situ sampling of the atmosphere of this remarkable world. I can't imagine it will be the last. Clearly, the organic chemistry that's occurring there today is of significant interest in terms of understanding the organic chemistry that might have occurred elsewhere in the solar system, such as here on Earth, before life began. One other place we can look in terms of understanding the organic chemistry that might have been important for the origin of life are the comets, of course. This is the Giotto image of Halley from 1986. By that time, it's just become clear that comets are charcoal black. They're covered with a charcoal black material, and when Giotto flew through the dust coming off of Halley, found that dust was comprised of material which was made of hydrogen, carbon, oxygen, and nitrogen. So the chemical building blocks of organic material. But there was no capability to analyze the nature of the material. Again, we need to take the next step of sampling. There are two approaches that are currently underway, one of which is in preparation, and that is a mission called Deep Impact, which would fire a roughly 500 kilogram copper projectile into Temple 1, creating an impact crater and analyzing the debris which comes out of that crater, as well as looking at the structure of the crater after the crater is formed. This mission is currently planned to do that on July 4th of 2005. That's an in situ sampling. There's also an opportunity to bring a sample back, which is already on its way. This is the Stardust mission. These are PI class missions. The Deep Impact is Brian Ahern, and Stardust is Don Brownlee, which is designed to capture some of the dust in the coma of a comet and bring it back to Earth. Of course, the challenge is doing that since we're not landing, we're just flying through, and to do that in a way that does not melt and evaporate the tiny dust particles. And to do that, we're using this aerogel material, a silicate material with a density about roughly 10 milligrams per cubic centimeter. So somewhat more dense than air, but not a lot more dense than air, so that the small dust particles when they embed themselves in the aerogel, will melt the aerogel rather than being melted. And these will then be recovered and returned to Earth. The encounter is planned for, with Build 2, it's planned for January of 2004, and the return to Earth is in January 2006. And so we will have a sample of thousands, perhaps millions, of tiny pieces of dust that have come off of a comet, and will be our first opportunity to analyze and detail what the molecular composition of this material is, and we can begin to answer questions like, where did this material come from, what is it, of course, and what role might it have played in the origin of life in the solar system. Well, sampling the solar system, there's one other object I want to mention, and that's the sun. This is a Yoko X-ray image of the sun, a few million degrees. The sun, of course, is the bulk of the material in the solar system. It is the benchmark for understanding composition in the solar system. The sample we're going to get is the sample that comes in the form of the solar wind. It's a mission called Genesis. Don Burnett is the PI for this mission. It will be launched this coming July. We'll be on station out in front of the Earth at the Lagrangian point for about a little less than 3 years, and we'll capture the solar wind on these disks of pure silicon. There's also a concentrator array in order to improve the sensitivity for even rarer species. So this sample will be back in about 3 years, almost 4 years from now, and will be a very accurate sample of solar material that comes to us in the form of solar wind. And as I said, that's the benchmark against which other compositions in the solar system can be compared. So sampling the solar system, both in situ and returning samples. The Stardust returning a sample of the comet, 2006, Genesis returning a sample in several years. Mars is in situ, at least in 2003, but eventually one would hope that within 10 years, one could imagine beginning to consider a sample return from Mars. Deep Impact, as I said, will do an in situ first sampling of the comet in July of 2005. So returning samples, well, first in situ samples and then returning samples will be very challenging, but it's a very critical step in pushing back the frontiers of geophysics as we characterize and eventually understand the remarkable diversity of the solar system, of the distinctive worlds that share the solar system with Earth. Thank you very much.